Hello guys, we want to start our 19th lecture. In this lecture, I want to talk about unit impulse function. We're going to define this function. Then we talk about Dirac delta function. And at the end, we want to find Laplace transform of Dirac delta function. So first we have to know what unit impulse function is. Unit impulse function usually is shown by delta A and is defined like this. It's equal to 0 when t is greater than 0 and less than t0 minus a. It's equal to 1 over 2a when t is greater than or equal t0 minus a, and it's less than t0 plus a, and again it's equal to 0 when t is greater than or equal t0 plus a. And in this case, a and t0, they are both positive, so a is positive and t0 is positive. If I want to plot unit impulse function, so here we have t-axis, here is delta function, unit impulse function. So here we have t0 minus a, t0 plus a. So when t is between 0 to t0 minus a, function is equal to 0. Here is 0. Then when t is between t0 minus a and t0 plus a, so it's equal to 1 over 2a. So here it's 1 over 2a. And after t0 plus a, again it's equal to 0. So in fact, it's the function. Why we call this function unit impulse function? Because if you find the integral of 0 to infinity delta a, unit impulse function of t minus t0 dt, so you can see that this integral is equal to 1. That's why we call this function unit impulse function. Why it's equal to 1? Because the integral is the area enclosed between function and t-axis. In fact, we have to find this area. So the length is 1 over 2a. If I want to find the area its length is 1 over 2a times its width. So here we have t0 plus a, here we have t0 minus a. As a result, the width is 2a. So times 2a, so it's equal to 1. In fact, the integral of unit impulse function over a range of 0 to infinity is equal to 1. It's unit impulse function. Dirac delta function is unit impulse function when a approaches 0. So we show you Dirac delta function with just delta. So it's delta t minus t0. It's in fact equal to limit of unit impulse function when a approaches 0. So in fact, if I want to show the Dirac delta function, so we have delta t minus t0, it's equal to infinity if t is equal to t0, and it's equal to 0 if t is not equal to t0. In fact, see this plot. Imagine a approaches 0. If a approaches 0, we have Dirac delta function, and its plot is like this. So here we have t-axis, here it's Dirac delta function at t equal to 0. So the function approach infinity. So in fact, Dirac delta function is a unit impulse function. As a result, the property of unit impulse function works for Dirac delta function as well. The integral from 0 to infinity delta t minus t0 dt is equal to 1. Dirac delta function has another property as well. So if you have the integral of 0 to infinity ft times Dirac delta function of t minus t0, this integral is equal to f at t equal to 0. It's property of Dirac delta function. For example, you want to find the integral of 0 to infinity, for example 2t times Dirac delta function of t minus 1 dt. So it's equal to 2t at t equal to 1. So it's 2 times 1, and it's equal to 2. It's property of Dirac delta function. So now we know unit impulse function, Dirac delta function. We want to find Laplace transform of Dirac delta function. In order to find Laplace transform of Dirac delta function, so we have to use this equation. So you have Laplace transform of Dirac delta function of t minus t0. It's equal to, I have to just close it. It's equal to e to the power of minus t0 times s. For example, you want to find Laplace transform of Dirac delta function of t minus 2 pi. It's equal to e to the power of minus 2 pi times s. Or for example, you want to find Laplace transform of just Dirac delta function. So in fact, it's Dirac delta function of t minus 0. So we have e to the power of 0 times s. So it's to the power of 0. So it's equal to 1.